Hi everyone, and welcome to Chapter 15 on chi-squared tests. Before we talk about specific tests, it's important to zoom out and look at the concept of statistics more broadly. Statistics are divided into two different types of tests, parametric and non-parametric. Parametric tests require assumptions about parameters, which refer to the population we are comparing them to. Parametric tests include tests like z-tests, t-tests, ANOVAs, and others. Everything we have done up until this point has been parametric. Non-parametric tests are an alternative technique for when assumptions of a parametric test cannot be met. The meme here is ridiculous, but it highlights the idea that these tests are for when we cannot run a parametric test. There are several different non-parametric tests out there, but in this lecture we will cover chi-square goodness of fits and chi-square tests of independence. So why would we run a non-parametric test? Well, first they allow us to test categorical variables like small, medium, and large. We don't need ratio or interval data to run these tests. Next, they allow us to have an analysis when the assumptions of a parametric test cannot be met. For instance, if we go through all of the work of collecting data and then find that it doesn't have equal variances for a repeated measures t-test, we don't have to throw out that data. We can just run a different test. Similarly, non-parametric tests allow us to run tests on data with unusually high variances. If we have a lot of outliers, we can still handle that data. And lastly, non-parametric tests are helpful when scores cannot be determined. Maybe some participants didn't finish the test, or if it's an animal study, a rat never found its way through a maze. Let's start with the chi-square test for goodness of fit. This test uses sample data to test hypotheses about the shape of proportions of a population distribution. So, in other words, does the data match the percentages found in a population? This means that instead of using means and standard deviations, we are examining frequencies and how they compare. Remember that at the beginning of the semester, we discussed the frequency distribution table, which allowed us to look at how often each score occurred. The example here on the screen shows frequency of eye color. With the chi-square, we are doing the same thing, but we represent it in a box like this one. There are two definitions you need to know before we jump in. The first being expected, or E, which is what we would expect the data to be. And this is based on previous research or some other rationale. And observed, or O, which is what the data we actually collected shows. For instance, say we want to run a study on therapist behavior, and we want to generalize it to the population. One of the questions we might ask is whether or not our sample of 100 therapists matches the gender parameters of the population. So, based on previous research, we know that about 75% of therapists are women and about 25% are men. We would expect that with random sampling, our data will match these proportions. The observed values are the data we collect. Does our data match these expected values? Or did we recruit only men for our study, which may indicate some concerns with generalizability? With this, there are 6 steps for solving a chi-square test, and this works for both of the chi-square tests we talk about in this lecture. The first is to state the hypotheses. The second is to set the critical value. Then we examine the observed frequency and identify the expected frequency. We solve, and then we make a decision. So just like before, we have two hypotheses here. Our null hypothesis states that there are no differences between the expected and observed proportions. Using the same example, our null hypothesis would be that the observed gender distribution of psychologists matches the expected distribution, such that 75% are women and 25% are men. Our alternative hypothesis is that the observed gender distribution of psychologists does not match the expected distribution. This means that if you are hoping for the observed and expected parameters to match, you are hoping for the null hypothesis. For now, I'll skip step 2 on finding the critical value because I think it's important to understand our data before we look at the distribution table. Say we look at our data, and this is the result. We find that in our sample of 100 therapists, we have 60 women and 40 men. And when you make these tables, make sure that the number of people in each category, notated as C, adds up to the full sample size and that we're not miscounting anything. The next step is to identify the expected frequency. As a reminder, these are the expected percentages. What I want to highlight here is the difference between percentage and frequency. Because we have 100 participants, our N for each category matches that percentage. But these frequencies would be different if we had, say, 50 participants. Taking 75% of 50, that would give us 37.5 women, and taking 25% of 50, that would give us 12.5 men. The takeaway here is not to confuse percentages for frequency. And now we can solve. The goal of the chi-square goodness of fit test is to examine the discrepancy between the observed and expected data. And we do this using the equation, the sum of the observed data minus the expected data squared divided by the expected data. So because we are adding the values in the chi-square formula, we can never get a negative value. We always have a one-tailed test. I find that the easiest way to solve is by making a table. Here are the observed and expected values. We can then subtract the expected value from the observed value, square it, and then divide by the expected value. We sum these numbers, and that gives us 12. The last step is to find the degrees of freedom, which is C minus 1. Again, C just stands for categories. We have two categories, women and men. 2 minus 1 is 1. To find our critical value, we use a chi-square distribution table, which is posted on Canvas. This table is pretty straightforward. We have a column for our p-value and a column for our degrees of freedom. So in our example, we have 1 degree of freedom. Using the 0.05 column, that would give us a critical value of 3.84. Our output was 12, which is larger than the critical value. So we reject the null. The observed gender distribution of psychologists does not match the expected distribution. And we notate this as chi-square with the degrees of freedom in parentheses equals the output, and p is less than 0.05. Here's a practice problem for you to try on your own. Based on previous data, a school counselor believes that students choose after-school activities in the following proportions: 40% sports, 30% arts, 20% academic clubs, and 10% other. Here are the observed numbers. Pause to solve. The answer will be shown in 5 seconds. Here are the answers to that practice problem. Pause to review, and please let me know if you have any questions. Moving into the chi-square test of independence. This test is different in that instead of comparing proportions to a population, we are examining whether there's a relation among variables, which sounds like tests we've run before, right? The difference is that chi-square tests for independence use categorical variables, as opposed to ratio or interval data. If you need a refresher on the types of data, please review the Week 1 lecture. In tests of independence, we are only looking at frequencies. So to give you an example of this, say we are interested in whether or not there is a difference in preferred learning mediums among males and females. We ask a sample of people if they prefer to learn through books or on the internet, and we just take a tally of these to compare groups. So let's go into the hypotheses for this test. The null hypothesis is that the variables are independent, meaning that there is no relation among groups, and we cannot predict who will fall into what category. The alternative is that the variables are not independent. In other words, there is a relation among groups. The chi-square test of independence is similar to the goodness of fit test. We still have a table with the observed and expected frequencies. But now we have multiple variables with different levels of each variable. So in this example, we have book versus internet, so two variables, and male versus female, so two levels. We would say that this is a 2 by 2 analysis. So with this, say we sample 80 people, and then these are the observed values. The problem moving forward is that we don't know what the expected frequency is. To find our expected values, we use this equation, where we multiply the total frequency in the column by the total frequency in the row and divide by n. Because we have multiple frequencies and rows, this means that our degrees of freedom also changes. Degrees of freedom is now the number of rows minus 1 multiplied by the number of columns minus 1. From here, let's find the expected values. We add up each of the rows and each of the columns, and then use the equation to find the expected values for each category. So for the male and book expected value, we have 40 in the row total and 27 in the column total. 40 times 27 divided by our total sample size, which is 80, we get 13.5. For female and book, we again have 40 in the row, 27 in the column, and divided by 80, we have 13.5. We do this for the next column, and we get 26.5 for male and online, and then again 26.5 for female and online. From here, we solve just like we did before, using the table with the observed values, expected values, and the observed minus expected squared over expected values. Again, we sum those numbers and we get 0.504. The degrees of freedom is row minus 1 times column minus 1. We have two rows and two columns, so this gives us 1 degree of freedom, making our critical value 3.84. Our output is less than the critical value, so we fail to reject the null. The variables are independent. Here's a practice problem for you to try on your own. A researcher wants to know whether caffeine consumption is related to sleep quality. The researcher surveys 40 people and records whether each person drinks caffeine, recorded as a yes versus no, and reports adequate sleep, recorded as good versus poor. The observed frequencies are below. Is there a difference between groups? Pause to solve. The answer will be shown in 5 seconds. Here are the results. Pause to review, and please let me know if you have any questions. The effect size for a chi-squared test of independence and a chi-squared goodness of fit test are the same. However, the test changes based on the number of variables and levels you have. So for a 2 by 2 chi-square test, meaning you have two variables and two levels, we use phi equals the square root of chi-square over n. But make sure to use caution when finding the effect size, because the chi-square statistic is already squared, so avoid squaring it again. From here, we have a range of outcomes based on strength, ranging from a small effect to a large effect. So let's calculate the effect size for the last example. It wasn't significant, so we don't need to calculate the effect size, but it's a quick one to calculate for the sake of example. The square root of 0.504 divided by 80 is 0.079, which is a small to medium effect. If the matrix is bigger than 2 by 2, we need to use Kramer's V, which is the same analysis but multiplies the degrees of freedom by n in the denominator. But if you remember, there are two parts to that degrees of freedom calculation. We have rows and we have columns. And sometimes with bigger matrices, there isn't always an equal number of variables and categories. In this case, go with the smaller of either row minus 1 or column minus 1. The interpretation is based on whatever that number is. The numbers shown here are for when the degrees of freedom equals 1, 2, and 3. In this class, we will not go beyond 3, but you might see some academic papers out there that do. Lastly, there are assumptions for a chi-square test. The first being independence of observations. Each observed score needs to be a different person. We cannot have a repeated measures design. Second is an assumption regarding the size of expected frequencies, where frequencies need to be greater than or equal to 5. Of course, we should aim for larger sample sizes when possible to increase our generalizability, but when we have fewer than 5 observations, that will extremely skew the results. And that is all I have for you. If you have any questions, please let me know.